Hello, everybody. Welcome to a new session of the seminar. It is a pleasure to present our invited speaker, Othmane Jerhaoui. He's a PhD candidate in ENSTA Institut Polytechnique de Paris. The title of the talk is Optimal Control and Viscosity Theory on Singular Spaces. So thanks, Othmane, for being part of this seminar. And the floor is yours.
Thank you, Alfredo. So, okay, so today the topic would be mainly discontinuous optimal control and also discontinuous viscosity solutions. And the discontinuity comes from the state space itself. So we're going to see what all of this means. So I'm going to begin with an introduction, introduce viscosity theory and optimal control problems, and then I'm going to talk about the main issue of this talk. And then I'm going to present the main result. I'm going to present some result of conversions of monotone schemes. And finally, I'm going to talk about some extensions that it's still a work in progress, but I thought it was worth mentioning since we're in some advanced stage right now. So let's begin with an introduction. So Hamilton-Jacobi equation is a PDE. So we have it's a derivative with respect to time of our unknown plus a certain function with values in R. So we call it Hamiltonian, and we have an initial condition that is going to be our cost in optimal control problem. So examples of such equations. So we have the transport equation, of course, and we have also the Econol equation, which is a nonlinear example of this setting. So the Hamiltonian could be very much nonlinear. And so, well, classical solutions to those kinds of equations might not exist and often don't exist. And so we need a notion of, let's say, a generalized solution. And for that, we introduced the notion of viscosity. So basically what it means, we take some test functions and we take the graph of those test functions. So if, for example, our test function, the graph of our test function touches the graph of our, let's say, candidate solution from below, then we get an inequality, let's say. We get that our PDE, when we replace the derivative with respect to time and the derivative with respect to space with the derivatives of the test function, we get a first inequality, which is inferior or equal to 0. And also, so we say if we have this first inequality, we say that our function is a subsolution. So the test function, the graph of the test function touches the graph of our candidate solution from below. And same way, if our candidate solution, we say it's a super solution, if when we take a test function and the graph of this test function touches the graph of our candidate solution from above this time, then we get the opposite inequality. So we get superior to or equal to 0, so of our PDE. So if we have both those inequalities for every test solution, then we say it's a viscosity solution. And of course, it has to verify the boundary conditions. So why do we use this particular notion? Because first of all, it was developed by a lot of authors, mainly Lyons, Souganidis, and of course, Ishii, Bao, Evans, and Jensen, and others contributed to the theory. And we use this notion, this particular notion, because it gives us existence, uniqueness, and stability of mainly nonlinear PDEs. And also, this tool is very useful in the treatment in the, let's say, theoretical study of numerical schemes. And it's also very useful for optimal control problems. So let's now talk about optimal control problems. So it's so first of all, we have a dynamical system that depends on some variable u, which is the control. And of course, we have our unknown, which is a trajectory x that lives in RD. So now we just consider the Euclidean space. And our control lives in, it's a measurable function that lives in a compact set, U. Well, for simplicity, we can just take it to be a subset of Rm for some m. And so an optimal control problem would be this minimization problem. So for our, let's say, dynamical system, we fix a t0 and x0, so which gives us the initial condition. And we want to minimize certain costs, which is g, so certain costs with respect to the initial condition, such that our dynamical system holds. So we minimize over all trajectories that are solutions to the dynamical system for some control u. And now if we vary the initial condition in the dynamical system, if you vary x0 and t0, then this minimum is going to vary also. And so when it's going to vary, it's going to verify a certain PDE. And this PDE is kind of a Hamilton-Jacobi equation. It's actually called the Hamilton-Jacobi-Bellman equation, so it's this particular case. And it's written in that way. So it's the derivative with respect to time of V plus the supremum on the compact set U of the derivative with respect to space of V scalar or applied to the dynamics. And also the initial condition would be our cost in the optimal control problem. So let's go back to some previous examples. So we have the transport equation. So the transport equation could be just written in a simple way where the dynamics is just a of x without any control. So so here the equation is linear, and the initial condition would be the cost over, let's say, it's going to be one trajectory basically. And for a more interesting example would be the Econon equation. So the dynamics would be just the control, U. And U would live in the compact space. Well, our compact space here, it would be just the closed ball, unit ball of some, let's say, here it's RD. Other examples that don't necessarily come from optimal control, we have the Isaac's equation, which are linked to differential games, and then we have the Burger's equation. Here in this equation, X, the state space, should be in R, so it's dimension 1. Otherwise, it's more complicated. So this is, in a nutshell, the viscosity theory on optimal control. Now I'm going to focus on the main problem. And I'm going to focus particularly on Hamilton-Jacobi equations that come from optimal control problems. So I did this long introduction because I wanted to emphasize the fact that all these examples are defined in the Euclidean space. So the state variable, which is the trajectories of our optimal control problem, they all live in RD. But we have a lot of interesting examples and applications where the state space is not necessarily a Euclidean space, and it's not necessarily a smooth space. Let's say it's not necessarily a Riemannian manifold, for example. So such example, for example, well, one interesting example would be the traffic flow. Like, just imagine that we have 4 roads, and we have the intersection of those 4 roads, and each road has its own flux, let's say, of cars. So each road has its own, let's say, dynamics. So which is going to give us a Hamiltonian that depends on this branch of our network, let's say. And because of that, so this space is not Euclidean. Of course, I mean we can clearly say it. We can clearly see it at the origin, which means at the intersection. So in this intersection, let's say the space doesn't look, even if we zoom in, let's say in the Riemannian setting, we take a local chart. If you do that, if you zoom in near the origin, you're always going to find a network, sort of X-shaped. space. So the question remains, because here we don't know how to define the derivative, because in the smooth setting, either we work with the gradient or with the differential. So here we don't have a clear notion of what is a derivative, what is a differential, or what is a gradient. So that's the question we are asking. Second, less intuitive example would be multi-engine systems. So in this setting, we have an optimal control problem with a very big number of players or agents here. So let's say the example I took is let's say a group of, or a herd of birds that are moving in a way that would minimize the energy when they travel. So when they migrate from point A to point B, in the sky, if we look at it carefully, they take certain configurations, and those configurations are actually have a let's say an objective, and the objective is to minimize the energy. And so when we modelize those kinds of problems, we suppose that the number of agents is very high. And thus, we consider those agents as sort of a density of some measure. And because let's say this density has a, let's say, constant mass, we can divide by the constant mass, and then we get just a probability measure. And so the state space here to consider, the right setting, would be the set of probability measures. The sigma algebra would be the Borel sigma algebra. And so we get, so this space, if we endow it with a particular distance, and I'm going to talk about it later, it's going to be called the Wasserstein space. And in this space, it's even less intuitive to describe the derivative. So what's a derivative with respect to a measure? So if we want to modelize all the movement of this group of birds, so it follows the dynamic, and this dynamic is going to depend on the derivative with respect to the state space, so with respect to a measure. And this is a less intuitive example, and we don't know. In first look, we don't really know how to do that. So I'm gonna talk first about the state of the art. So for the first example, in the literature, you could find those kinds of problems under the name of regional optimal control problems, which were treated by many authors. So Hassan and Wong were the pioneers, the first ones, and then Hermosilla, Wolensky, and Zidani, and so on. And then for the viscosity approach on those kinds of spaces, so let's say stratified spaces, there is Zidani and Zipin Rao, and then Barl and Chesson, Hermosilla and Zidani also, and a lot of other authors. And then for networks, which is mainly the example that I showed, it was done by Barl, Ashtou, Lyons, and Souganidis for just one-dimensional case. So networks in 1D. So we don't have, like, for example, planes glued together or such. So mainly the one-dimensional case. For multi-agent systems, we have those are very recent problems, very, very new problems that were treated in 2019, 2020. And it was done by Bonnet, Marie Gondac, Ancompra, Gardaliaghi, and others, of course. And now the question we are asking, we are treating, so we want to have let's say, a general theory of Hamilton-Jacobi equations in those spaces, and the link between those two spaces, because at the first glance, we see that a network and the space and the Wasserstein space, the space of probability measures, are very different. Yet they're not that different, and we're going to see why. So I'm just going to present, At first, I'm going to talk mainly about stratified spaces or networks. So mainly because the talk is, well, I'm going to need a lot of, let's say, tools of viscosity theory, and mainly if I have to talk about the subject in all its generality, I'm going to need some heavy tools, let's say, very technical tools of metric geometry. I'm going to talk about them briefly at the end, but for now, I'm going to just concentrate on Hamilton-Jacobi-Bellman equations. I'm going to take a simple one-dimensional network of two branches. Let's say it's an intersection of roads, but just two roads. So here's the setting. So we have, let's say we have just this one-dimensional Euclidean space R, and I'm going to divide it into three regions. So you have R plus, R minus without the origin, and then the origin itself I'm gonna consider it as a region, as a different region. So it's let's say the boundary between those two regions. So now, as I said in the example of networks, on each branch I'm going to take some sort of dynamics, and here I'm going to use the notations from non-smooth analysis. So I'm going to consider a set of dynamics, so which is just the set of all let's say velocities with u going through the set of ui. So it's a compact set ui. So for the first region, for omega 1 and omega 2, so r plus and r minus without the zero. So we have the optimal control problem like this. So we'll go the same way. So we're going to minimize a certain cost with respect to all trajectories that verify the let's say the dynamical system that we have. Notice here that the dynamical system is just defined on each, let's say, on omega 1 and omega 2, and so with the field of Pov regularization, we could define the set of trajectories on all the space, and the Hamilton-Jacobi equation that is associated to it. So on each region, we have the Hamilton-Jacobi-Bellman equation that is classically defined with the initial condition, which is the cost. The problem here is that the equation is not defined at the boundary or at the origin or at the intersection gamma. So the first attempt would be to convexify at the origin. So we're going to take all the set of dynamics from both, coming from both, let's say, roads, from both branches, and we're going to take the convex hull of both of those dynamics, set of dynamics. So the trajectories, like I said, are described that way. So we have the dynamics, we have the velocities from both branches, and then at the origin we convexify, and that's how we describe the velocities for all this space. So if we do that, we're going to have at the origin, we're going to take the Hamilton-Jacobi equation at the origin with respect to the velocity f, the set of velocities f gamma. The problem with this approach is that with this trial, let's say with this attempt, is that the dynamics are too big, which means that this equation does not characterize the value function, which is the solution to our optimal control problem, because the dynamics are too big. So the value function is not a solution to this equation. So the second attempt, we will only consider the essential dynamics. So what are the essential dynamics? So first I'm going to talk, so the essential dynamics are the directions or the velocities that stay at the tangent cone. So for example, for omega 1, the tangent cone in any point without any point but the origin would be just r. So the dynamics are free, let's say, on each branch without the origin. But at the origin, we're gonna just take the half, let's say the half space. So for example, for omega 1, we're just gonna take at 0, we're gonna take the tangent cone to be just r plus. The same way with omega-2. So omega-2 bar, of course, because we're going to go until the origin. So with at any point but 0, we have free dynamics, which means that we're going to take the whole set. But at 0, we are going to take just the half space R minus. That's the tangent cone here, because we have a simple example. If you take the Polygon tangent cone or Clark tangent cone or any other one, they're equal. I'm going to talk maybe briefly about the differences, but if we have some hypotheses on the stratification of this decomposition, they're all the same, basically. So the essential dynamics differ only at the junction, because at any point but the junction, we take the tangent cone would be just the whole space, which means that we have no restrictions on the velocities. We only have restrictions on the velocities at the origin or at the junction point or the intersection. So that's why we are going to take the essential dynamics to be the following. So at the junction, we're only going to take the velocities which stay at the tangent cone. So we're going to intersect, for example, F1, which is charge dynamics related to omega-1. We're going to intersect them we're going to take only the ones that stay at the tangent cone. Same thing with F2, and we're going to add to that the velocities that are coming from the Filipov regularization intersected with the tangent cone of gamma. And the tangent cone of gamma is just 0 because it's the 0 point in this example. So if we do this, we define the essential dynamics this way. It's the union of all those 3 dynamics, sets of dynamics. And the trajectories now might differ, because in the beginning, we said that the set of trajectories are defined by the Filipov regularization. Here it's a smaller set. We take only the essential dynamics. But luckily for us, the 2 optimal control problems are the same. Well, let's say the 2 dynamical systems are the same, even if we take a smaller set of dynamics. But so the dynamical systems are the same, which means that the optimum control problems are the same. So it's the same thing, defined the same way. And now we can define our Hamilton-Jacobi equation. So it's the same thing at omega-1 and omega-2, but at the boundary, let's say, or at the junction or at the intersection of those branches, we're going to take the essential dynamics. So because it's the union of those 3, you could write the supremum over the essential dynamics, or you can write the maximum the maximum is running through 1, 2, and gamma of the supremum of each set of dynamics, let's say FE1 and FE2 and FE gamma. So I'm going to use that in later. So this is just a notation. So the supremum over the set of essential dynamics. So if we do that, the question remains, because now in this example, I just treated the example of 2 branches. So let's imagine if we do the same thing, but with 3 branches. So the question still remains, how do we define the derivative with respect to this to x, let's say the spatial derivative at the junction? So here, because of this construction, it becomes clear, or at least we have an intuition, that the directional derivatives are the ones that are important and not the differential itself. Which means that because at the junction, we only took the essential dynamics, and the essential dynamics are kind of directional derivatives. So you only take the derivatives with respect to those velocities or those directions. Which means that maybe at the junction, we need to take test functions that are not necessarily C1, but we take test functions that are just directionally differentiable at gamma, so at the boundary, at the junction, sorry. So the idea would be to take test functions that are C2, but on each branch. So before we saw that the test functions were C2, here we're going to relax that hypothesis a little bit. Let's say that that set of test functions. I'm going to take just test functions that are C2 in each branch. So taking all of this into consideration, we can have a result of well-postedness, which means that we have, so if we suppose that the sets of dynamics are Lipschitz continuous, they have linear growth, and they have full controllability near the junction, which means that there is a small closed ball that is that belongs to the set, to each Fi, so to each set of dynamics. So then the Hamilton-Jacobi equation that I defined with the essential dynamics has a unique viscosity solution. And this viscosity solution is the value function that is given to us by the optimal control problem. And also the second theorem that we have is, and this one is going to be very useful for numerical analysis. This is the comparison principle. So if you take U1 and U2 lower semi-continuous super solution and upper semi-continuous super solution, and they verify that, well, and such that they're at t equals 0, we have this inequality. So the super solution at t equals 0 is inferior to the sub-solution at t equals 0. Then this inequality is valid for every t, which means that U2 is inferior to U1. So if we have that at the, let's say at t equals 0, we have that everywhere. And so, and keep in mind that the test functions here are piecewise C2. So they're not C2 everywhere, but C2 on each omega I and also on gamma. But in this example, it's just a point. So it's going to be a constant. So with this comparison principle, we could have a convergence result of monotone schemes. So we keep the same stratification, we keep the same setting. I'm just going to change a little bit the notations. I'm going to name omega 1 M1, omega 2 M2, and gamma, I'm going to name it M3. And so I'm going to take a spatial grid, a regular spatial grid for each, let's say, domain. For M1 and M2 and M3. So M3 here is just a point, but it works the same for a general case. And I'm going to suppose that, for example, if we have a regular spatial grid for gamma, so for M3, and I need a compatibility between those two spatial grids. Mainly, I need that the points of discretization of gamma, I need it to be included in the spatial grid of omega 1 and omega 2. So this hypothesis means that it's just the grid, let's say the spatial grids are compatible. So if we have a domain that's included in the other one, the spatial grid of that domain is also included in the spatial grid, the spatial grid of the other one. So that's what the hypothesis CC means. Like it's just a compatibility hypothesis between spatial grids. We also take a regular time grid. So for R plus, and we will take an approximation of each Hamilton of each, let's say HI. So we're going to see what SI is. So it's basically it's just an approximation of our Hamilton-Jacobi equation. For example, on omega 1, S1 is going to approximate the Hamilton-Jacobi equation, Hamilton-Jacobi-Bellman equation on omega 1 as we wrote it. So we're going to see the hypothesis. So we have, so those SI, so those approximations, they verify some standard hypotheses. So monotonicity with respect to the last variable, which in which we put the interpolation of the numerical solution of the points that we find in our numerical scheme. And so UH here is going to be an interpolation between the points that we find numerically. So here, let me go back. So THXH and UH, well, here it's going to be like THXH also. I forgot to write it. So we have UH, TH, and XH. and we take an interpolation of those points to get UH. So it's just an interpolated function. So, and we suppose that this UH is locally bounded and Lipschitz continuous. And we suppose it to be Lipschitz continuous on a neighborhood of the interfaces, which means on a neighborhood of M3 in our case. So we take this UH and we want it to be Lipschitz continuous bounded everywhere and Lipschitz continuous on a neighborhood of M3. And this Lipschitz constant should not depend on H. And that's the thing that we add. This is what we require more from the classical case. And of course, the consistency, which means that our approximations, let's say the SI, are going to converge to our Hamilton-Jacobi equation. So here HI, let me go back. So for H1, it's related to M1, so it's related to to the set of dynamics FE1, so the essential dynamics 1. For S2, so it's going to be related to H2E, which means the set of dynamics that F2E. But for the third one, it's going to be the essential dynamics related to gamma. So that's H3. So H3 is like HF gamma E. Well, the essential dynamics related to gamma. So if we have that, and so see that at the boundary here, I take the maximum of those 3 approximations. And why I do that? Because I take the supreme over all the essential dynamics, and the supreme over all essential dynamics means that it's the maximum of the supremum of the dynamics of each, let's say, MI. So if I have that, I have this theorem that that resembles the theorem by Barl and Souganidis, proved in the 80s. So we suppose that our original equation, Hamilton-Jacobi equation, admits a viscosity solution, which is continuous. And we suppose that for all, let's say, time step and spatial step, we have a solution to our numerical scheme, UH. And also we have that the grid verifies this, the spatial grid verifies this compatibility hypothesis. And then the last thing is that the approximations here, SI, verify the hypotheses of monotonicity, stability, and consistency. If we have all that, then we have that the approximation, the UH converges locally and uniformly to U. So the proof is exactly the same as in the classical case for Barl and Souganidis. The only thing we suppose more is this one. So we need to have Lipschitz continuity uniformly with respect to H near M3. So now we will discuss some extensions. So what, and in here I'm going to talk a little bit about the Wasserstein space. So first of all, I'm going to talk about Alexandrov spaces. So Alexandrov spaces, you can think of them as a generalization of Riemannian manifolds. So Riemannian manifolds are smooth, let's say, surfaces or hypersurfaces. You can imagine them like that. Here, an Alexandrov space would be a geodesic space or a metric space. A geodesic space is a metric space where at each 2 points, we can find a geodesic that goes, that actually links them. So for each X and Y, we can find a geodesic between X and Y. So that's a geodesic space. We only need the metric. And we say that a geodesic space is an Alexandrov space if we have 2 topological features, one locally compact and the second one is complete. And the third condition, which is more related to geometry, is so this space should have either a curvature bounded from below locally, or it should have a curvature bounded from above. So now the notion of curvature here is different. So it relies more on some intrinsic way. So I'm going to be vague about the notion of curvature here. But for example, if you take a Riemannian manifold, for example, so if you have sectional curvatures, for example, that are bounded above or bounded below, you get that the Alexandrov, let's say, curvature is also bounded above and or bounded below by the same constant that you will find in the smooth case. Let's say, for example, we have a sphere. So you take a sphere, a unit sphere. So it has a constant. The sectional curvatures of a unit sphere is 1, which means that you could actually think of a sphere as a space which has a curvature bounded below by 1. So the curvature would be bounded below by 1. It also means that the Alexandrov curvature of the unit sphere is also bounded below by 1. But the notion of curvature could be here generalized to all geodesic spaces. So examples of such settings, for example, you have convex polyhedra. So if you take convex polyhedra, you will find that the curvature here in the sense of Alexandrov is always superior to 0. So for example, if you take just a rough sphere, so it's a sphere, but you have some, like it's cut out, let's say, a little bit. So it looks like a sphere, resembles a sphere, but it's not smooth. So that's an Alexandrov space with curvature strictly, well, curvature superior to 0, strictly positive even. So for a network is the other way around. A network would have a curvature that is inferior to 0. The reason why is related to let's say, the definition of curvature in Alexandrov space, in an Alexandrov sense, but we can define a curvature for this space, and the curvature is inferior to 0. So if we have those kinds of, those are 2 examples, and you could already see that they kind of look like the state space of our problems. So the third example would be the Wasserstein space. So you take M to be a compact Riemannian manifold. So the curvature here would be superior to 0, strictly, because the sectional curvatures would be superior to 0, which means that the Alexandrov curvature as well would be superior to 0. Because compact Riemannian manifolds are special cases of Alexandrov spaces. So we take a compact Riemannian manifold with empty boundary, and we take D as its length distance. So the Wasserstein, well, the set of Borel probability measures of M, we're going to note it to be PM. And we define a coupling of 2 measures. That if you take mu and nu, and those are 2 probability measures that belong to the Borel probability measures of M. And we define what's called the coupling between those 2 measures. So a coupling is just a measure on the product space of M cross M. So it's a probability measure in M cross M, such that let's say the image measure of gamma with respect to the first projection would be mu, and the image of gamma with respect to the second projection would be nu. So that's a coupling between 2 probability measures of M. So the Wasserstein space is defined as the metric space, the PM, so the set of probability measures that we equip with a certain distance. So the distance is defined this way. So the distance squared between 2 measures, mu and nu, would be the infimum over all couplings that, so the infimum over all couplings of the integral over the product space of the distance. So you take the integral of the distance square. So the distance here is the distance of the Riemannian manifold, the distance square, and you integrate it with respect to a coupling of mu and nu. So the infimum over all couplings is always reached. So this is called the Kantorovich problem in literature, and it's always reached. And this quantity is actually distance. So it verifies the axioms of a distance. And if you equip the set of probability measures with this distance, this set is an infinite dimensional compact Alexandrov space. So it's not only locally compact, but also infinite dimensional. So what I want to say is that So the link between those two sets, like I said, is this Alexandrov geometry. And this, let's say, this generalization would allow us to treat both examples, let's say a network, convex polyhedra, and Wasserstein spaces the same way. So the goal here, again, I'm going to go back to the question. So we saw that only directional derivatives are important. So this is the intuition that we had from networks, that only directional derivatives actually matter. The problem is that if you want to look for test functions in let's say Alexandrov spaces, it's kind of difficult, mainly because first of all you have to define a notion of directional derivative, and not only a notion for, and more so you have to have some kind of regularity of the differential with respect to x. Let's say if you find the directional derivative at a point, you have, if you vary the point, you have to have some kind of regularity. So ideally you would have it to be continuous, and then you would say that it's C1 in the classical case, but usually you don't have this. And so the second thing you would look for is Borel measurability and so on. So you need some sort of regularity of the differential itself. So the difficulties are the following. Alexandrov space don't have smooth structures. There is no local charts, there are no local charts, parallel transport doesn't exist, and tangent bundles don't exist. Which means that let me go back to networks or convex polyhedra. In networks, in any point but the origin, the structure is Riemannian, because if you zoom in at any point but the origin, you're going to have just R. So the tangent space or the tangent cone is just R. The problem is always at the origin. The same thing for convex polyhedra. If you zoom in almost everywhere, except at the, let's say the vertices, almost everywhere it looks Riemannian, but it doesn't have any smooth structure. So actually the same thing applied for PM. There is a general Riemannian structure that we could define on this space of probability measures. So it's the work of Gigli and others. But again, we don't have smooth structure. So that's the difficulty. The difficulty comes from here. So we don't have smooth structures. So it's very difficult to define the notion of differential, let alone the regularity of the differential. And also the second problem is there is no clear way to define optimal control on those spaces. So if you take a stratified space, for example, a network. So in a network, you could define the dynamics on each branch. Good, and then you could define the set of solutions by the Filipov regularization, or that's how we usually do it, or maybe even with the essential dynamics. In, let's say, the Wasserstein space, for example, people are starting to work on it, but there's no clear way, or let's say a classical way, or to define optimal control problems on those spaces. So I'm going to end up with some conclusion and perspectives. So what have we done so far? So we defined a new notion of viscosity for Hamilton-Jacobi equations on networks. Which guarantees well-posedness and also a comparison principle. We proved conversions of monotone numerical schemes, like the same way as in the classical setting. What we also did is that there is a those regional optimal control problems. They take place in a state space which is stratified. So the same notion of viscosity also works. And for this general class of non-Euclidean spaces, namely the Alexandrov spaces, we also have, for now, we have a notion of viscosity, but it's still a work in progress because it's not submitted yet. Future work would be to continue to work on multi-agent systems, namely the space of probability measures, so the Wasserstein space. And also, we would like to have, let's say, a kind of a theory for this a theory of optimal control problems on those Alexandrov spaces, which is not done. I mean, people work only on Wasserstein spaces at this point. So which is a very special case of Alexandrov spaces. And that's it for me. Thank you for your attention.
Thanks a lot, Othmane. So now I wonder if the participants have a question. Any question? Christopher?
Hi, I have a question. Hi, Othmane. Nice to meet you.
Oh, nice to meet you too.
So I have a sort of question, but
Yes.
in your assumptions, you assume controllability at the singularity.
Yes.
So do you have an idea what could happen if not?
I think I have an answer. I mean, I don't just assume controllability at the junction. I assume controllability near the junction. So at the neighborhood of the junction. So which is even more stronger. And it actually, you could show that it's kind of equivalent to the coercivity assumption on the Hamiltonian. And for general, if you take any dynamics on branches, generally speaking, you don't have well positiveness. I mean, you could find counterexamples.
Yeah, but you mean well positiveness in the sense of continuous solutions. I mean, this is
yes.
the point, what I mean. Because even though I mean, my impression is that when you have this controllability assumption at the end, you have the same, at the end, the problem with the convexify, the kind of Philipov convexification at the origin are the same problems, I think. You're not introducing more dynamics at the end, I think, because the controllability is too strong, I think. So
it is strong. It's the same thing as coercivity, because both hypotheses, you need them to. There are sufficient conditions, but it's very strong indeed. You need them to guarantee solution, but yeah.
Yeah, but for instance, you can use the same to look for solution on the lower semi-continuous solutions only. But in that case, the numerical scheme you have studied,
yes,
I guess it will work anyway. But do you have an idea to what it will converge?
Yeah, that's a good question. I tried that on. I tried some simulations on some dynamics that are not necessarily fully control. We don't have full controllability near the junction, and usually you don't converge. I noticed that. I noticed that you converge to something, but it's not necessarily the solution. And one way to see it is. What I do is I try to have let's say, I take let's say a linear dynamic, and this linear dynamic I try to make it to be like zero, but not at the origin. So not really linear, but like let's say piecewise linear. So if you take, for example, on omega-1, you take some sort of, let's say, an equivalent equation, but the radius tend to zero, will tend to zero at the origin. And so, and this, let's say the radius of your ball that you take is going to change also, let's say in the interior of omega-1, but it's going to also tend to zero. It's going to be zero at some point in omega-1, but not the junction as well. So it's going to be zero at the junction and zero in another point, but the junction, and in between. So you are going to realize that at some point you're going to have some discontinuities that are not necessarily, well, you're going to converge into something that is discontinuous, but not necessarily the value of function.
No, I understand that. The point is that to what you might converge. I mean, will you converge, for instance, to the some sort of continuous envelope of the value function, or because I think these numerical schemes, when I'm not expert on that at all, but what I hear is that at least when you have this monotonicity and consistency assumptions, at the end, you ensure that it doesn't matter what you converge to, the limit is a continuous function. So at the end, this numerical scheme always regularize, it will always give you something that is continuous, even though the problem could be anything.
In the stratified setting, it doesn't give you continuous. I tried it with a network of 3 half lines.
No. I was talking in the
classical case.
Classical case, you have that.
Yeah.
So I don't know if in this stratified setting you will get something similar to get as well something that is continuous.
Yes. Well, from the few tests I did, first of all, you don't always converge to something continuous, and sometimes you don't know to what you converge to. I don't. Maybe it's like you said, the convex envelope of the value function, but I really don't know. It's really an open question. I didn't do a lot of tests, to be honest. I did some basic tests on let's say a transport equation or an equivalent equation on each branch. With let's say the dynamics of the equivalent equation would change continuously, or maybe even in a Lipschitz way. And yeah.
Okay. Yeah. And the other question I want to do is
yes,
because I'm not in your future work. You're mentioning to establish some optimal control setting for this problem on Alexandrov spaces.
Yes.
So, what is the idea behind? Because
well,
do you want to have an interpretation of the equation to say that when you have that is strictly related, or because I mean in a Hamilton-Jerhaoui classical case, if you have a Hamiltonian that is convex on the p variable, you can always construct an optimal control problem that represent that equation at the end. More or less.
Yes. Well,
so
here
this is more or less what you want to have.
Yes. So the real goal is to treat Alexandrov spaces in a very abstract way, which means that maybe you could, okay, if you take a Riemannian manifold, just not a sub-Riemannian manifold, just a Riemannian manifold, you could define an optimal control problem on a Riemannian manifold in an abstract way, and you could have a Hamilton-Jacobi equation on this space, and you could also have a notion of viscosity on this space. See, now if you take a network, we always assume that a network is kind of immersed in some Euclidean space. My belief is it's the wrong vision. I think that you should consider the network as the network, the same way you would consider a sphere just a sphere. And from this, so we started to work on this. We just detach ourselves from any Euclidean structure, and the question raises itself: if you don't have let's say a Euclidean ambient space, how do you define an optimal control problem? So that's the real question. And for now, we don't have a clear answer, although in Wasserstein spaces, there are several, let's say, attempts and people are working on it. In Alexandrov space, it's less obvious for several reasons. The most important one is because you don't have a tangent bundle. So you don't have this. You don't have a smooth structure. You can define a notion of tangent cone in a very abstract way, like, for example, on a network. So in a network, you take the polygon tangent cone for each branch. And if you take the union of those tangent cones for each branch, you will get the tangent cone at 0. So this construction, you could have it in a very abstract way. So you could define a tangent cone at 0, and this tangent cone at 0 would be the union of the polygon tangent cones of each branch, basically. And this let's say simple example. And you could do the same construction for convex polyhedra. You could do the same construction for Alexandrov space, for Wasserstein space. Sorry. So the goal for us would be to have let's say a theoretical framework where you could work with those kinds of spaces without having the need for an ambient space. I don't know if I answered your question.
Yeah, no, I understand, but I mean, it's since you have the question, because in general, I mean, for me, the motivation to understand Hamilton-Jerhaoui equation is because you start from an optimal control problem. Now, for the PDE people, the interest is on the Hamilton-Jerhaoui equation itself. But now here you have already or people are studying Hamilton-Jerhaoui equation on these spaces. But I don't see a clear motivation to find a control problem that represents that, because at the end I mean it's more like somehow you encounter an optimal control problem, and then you want to see the ways to solve it. But it's not the way around, that you have a solution and then you want to see. I mean, this is more or less my question. Just curiosity.
I do understand what you're saying. So in Wasserstein spaces, for example, people, so the multi-agent problem is already defined. And also you could have mean field games that are defined on the same space, more or less. So you kind of have some optimal control problem in a way or another, and you want to have the viscosity solutions related. So now the Wasserstein space is only an example of those kinds of spaces, because we have the networks, we have the convex polyhedra, and you can, because they look so much Riemannian, so it's really it's more like an abstract question. Can you define dynamical system, first of all? And so if you can define that, so could you make it depend on some control, some parameter u, and it will give you an optimal control problem? Does this problem have solutions? If so, if you take the minimum of some costs over those sets of trajectories, would you verify a certain, let's say, PDE in this rough space, because this space is not smooth? And well, yeah, I agree. It's more of a, let's say, something abstract at the moment. The only applications we could think of are the networks, the polyhedra, and Wasserstein spaces. But maybe we will find other examples.
Well, yes. I think there is a small difference, which I don't know what is the role, but because in these examples you are showing, except the Wasserstein spaces are finite dimensional, even though if they are Riemannian manifolds, they are finite dimensional spaces.
Yes.
But yes, the Wasserstein case is an infinite dimensional case.
Yes.
And when you have optimal control problems in infinite dimensional spaces, things become a little bit more complicated. Even if you consider, for instance, optimal control of PDEs.
Yes.
Things are different, because essentially you have many ways to define a control problem.
Yeah. Yes. But
it's not that obvious, I think.
Yes, but here the advantage is, if you take a compact Riemannian manifold, and in general, if you take a compact set, and you take the Wasserstein space over that set, the Wasserstein space itself is compact, which means that you could actually have it's not a bad space in itself, like, because we have compactness, you could do more things. So if I take it on Rn, if I take the Wasserstein space over Rn, that's not a very good space, because you don't have local compactness. But here, because it's compact, even though it's infinite dimensional, it's compact. So you could more or less work on it. That's my point.
Okay, I see. Well, thanks. I won't continue, because I may take too much time. So maybe we can discuss in other occasion.
Yeah, no problem. No problem. Thank you.
Any more questions? Well, okay. There are no more questions, so I'm sure a lot of people will enjoy your talk when we share it on the social media of our department. So thanks again, Othmane.
Thank you for inviting me.
And thanks the participants for attending this seminar. So, bye.
Thank you.
Oh,
Bye.
Alfredo.